Hello everyone, welcome to SleepSpace. Tonight, we will talk about everything we know about the moon. Whether you're here to gently drift into sleep or simply relax your mind, you're in the right place. Let's begin our quiet journey across the history, mystery, and science of Earth's closest neighbour, the moon. For thousands of years, the moon has been a subject of fascination, awe, and curiosity. It has guided our calendars, inspired myths, and lit the night sky with its gentle glow. But what exactly is the moon? Where did it come from? And why does it behave the way it does? Let's start with the basics. The moon is Earth's only natural satellite, meaning it orbits our planet in a predictable path. It's about 2,159 miles in diameter, roughly one quarter the size of Earth, making it the fifth largest moon in the entire solar system. Though it appears to shine in the night sky, the moon doesn't emit any light of its own. What we see is actually sunlight reflecting off its rocky surface. The moon orbits Earth at an average distance of about 238,855 miles, which means it's close enough to influence us in noticeable ways, from the rise and fall of ocean tides to the rhythms of sleep and emotion in human beings. But we'll get deeper into that in a later part. Now, let's talk about its surface. The moon is dry, dusty, and heavily cratered from billions of years of collisions with asteroids, comets, and other space debris. Unlike Earth, it doesn't have a protective atmosphere to burn up incoming objects. This makes the moon something like a museum of the solar system's violent past, a frozen record of impacts that stretch back more than 4 billion years. Some parts of the moon are incredibly ancient. The dark patches we can see with the naked eye, known as Maria, from the Latin word for seas, are actually vast plains of solidified lava. They were formed by massive volcanic eruptions billions of years ago. In contrast, the brighter areas are called the lunar highlands. These are older and more heavily cratered, made of a lighter type of rock called anorthosite. Despite its apparent simplicity, the moon is a complex and dynamic place. It undergoes constant change, not through weather like Earth, but through what scientists call space weathering. Solar radiation, micrometeorites, and the continual bombardment by cosmic particles slowly alter the surface layer, creating a very fine dust called regolith. This regolith is unlike any soil we know. It's sharp, powdery, and clings to everything. During the Apollo missions, astronauts found it extremely difficult to remove from their suits, and it even caused damage to their equipment. Despite being dry and lifeless, the moon's surface has secrets waiting to be uncovered, including the possibility of water ice hidden in deep, permanently shadowed craters near the poles. Let's go back in time. How did the moon form? The most widely accepted theory is called the giant impact hypothesis. According to this theory, about 4.5 billion years ago, not long after the formation of Earth, a Mars-sized object scientists call Theia collided with our young planet. The impact was so massive that a portion of Earth's outer layer was blasted into space. This material eventually coalesced under gravity to form the moon. This theory explains many things: the moon's composition, its orbit, and its relatively small iron core compared to Earth. Samples brought back from the moon during the Apollo missions support this theory, as lunar rocks share many chemical similarities with Earth's mantle. And speaking of the Apollo missions, let's pause for a moment on one of the most iconic achievements in human history: the moon landings. Between 1969 and 1972, NASA's Apollo program successfully sent 12 astronauts to the moon. The very first, Neil Armstrong, took his historic first step on July 20th, 1969, uttering the famous words, "That's one small step for a man, one giant leap for mankind." The astronauts brought back not just rocks and data, but a renewed sense of wonder about our place in the cosmos. They walked on alien soil, planted flags, deployed scientific instruments, and photographed the desolate beauty of the lunar surface. Their discoveries shaped our understanding of lunar geology and the early solar system. One surprising find was the moon's complete lack of atmosphere. This means no weather, no wind, and no sound. It also means extreme temperature swings from over 250 degrees Fahrenheit in direct sunlight to minus 250 degrees in the shade. This lack of atmosphere is why footprints from the Apollo astronauts are still perfectly preserved. Nothing erodes them. Another intriguing fact: the moon is slowly drifting away from Earth. Every year, it moves about 1.5 inches farther from us. Scientists believe this has been happening for billions of years, gradually slowing Earth's rotation in the process. In fact, Earth's days were shorter in the distant past, about 18 hours long, because the moon was closer and its gravitational pull was stronger. Now let's talk about lunar phases. The moon's appearance changes throughout the month, moving through a cycle we call the lunar phases. New moon, waxing crescent; first quarter, waxing gibbous; full moon, waning gibbous; last quarter, and waning crescent. This cycle takes about 29.5 days, and it's caused by the moon's orbit around Earth and how sunlight hits its surface from our point of view. Interestingly, the same side of the moon always faces Earth, a phenomenon called tidal locking. This means there's a far side of the moon we never see from Earth. It's not permanently dark, as some might think. It experiences day and night just like the near side, but it was completely unknown to humanity until spacecraft began to photograph it in the 20th century. The far side is rugged and heavily cratered, quite different from the side we see in the night sky. The moon also plays a powerful role in Earth's tides. Its gravitational pull causes the oceans to bulge, leading to high and low tides. This subtle influence helps regulate life on Earth, from the behavior of marine animals to the ancient rhythms of planting and harvesting crops. Culturally, the moon has inspired myths, legends, and art across every civilization. It has been seen as a goddess, a god, a guiding light, and even a trickster. People once believed that the full moon could affect mood, sleep, and even human behavior, hence the word lunacy, derived from lunar, the Latin word for moon. Yet today, the moon is no longer just a symbol or a mystery, it's a destination. Space agencies around the world are planning new missions. NASA's Artemis program aims to return humans to the moon and establish a sustainable presence there. Other countries, like China and India, have launched lunar orbiters, landers, and rovers to study its surface and search for water ice. Why return to the moon? Because it holds answers. Answers about Earth's history, the origin of the solar system, and how to live on other worlds. The moon could one day be a staging ground for missions to Mars and beyond. Its surface might even host a permanent base, with solar power, mining operations, and scientific labs. And yet, for all its science and potential, the moon remains what it has always been: a silent companion, a glowing orb that follows us across the night sky, a presence that feels both ancient and personal. We look up at it and feel a connection, as if it's watching over us in the dark. As we begin this deep dive into the many dimensions of the moon, its formation, surface, science, and future, let its quiet constancy guide us through the cosmos. Close your eyes, if you wish. Let your thoughts rise gently like the tide, carried by the pull of the moon. To truly understand the moon, we have to go beneath the surface, not just literally, but scientifically. Its terrain, its chemical composition, and its geologic history reveal a story 4.5 billion years in the making. What seems like a cold, dead world is actually a rich geological archive, a time capsule of the solar system's earliest days. The Moon's surface is divided into two primary types of terrain, the lunar highlands and the lunar maria. The highlands are older, brighter, and heavily cratered, formed from anorthosite, a rock type rich in calcium and aluminum. These are the oldest parts of the Moon, over 4 billion years old, and they dominate the far side. The maria, on the other hand, are younger and darker. They consist mainly of basalt, a volcanic rock rich in iron and magnesium. These plains were formed by ancient volcanic eruptions that flooded giant impact basins, creating smooth, dark surfaces that can be seen with the naked eye from Earth. The maria are found mostly on the side of the Moon that faces Earth, a quirk of geological and gravitational evolution. The contrast between the highlands and maria was one of the first mysteries early astronomers noted. Before the age of telescopes, people thought the darker regions might be seas or lakes. That's why we still call them maria, Latin for seas, even though they are bone dry. But what caused these enormous lava flows? It turns out that after the Moon formed, its interior remained hot for hundreds of millions of years. This heat came from several sources: the energy of formation, the decay of radioactive elements, and the continued bombardment by space debris. This internal heat caused volcanic activity, though of a very different sort than we see on Earth. Instead of towering volcanoes, the Moon's eruptions were more like fountains of lava that spread across low-lying basins. These lava plains solidified into basalt and created the vast, dark maria. They are relatively smooth compared to the cratered highlands, though they still contain numerous impact marks. The youngest of these flows are about 1 billion years old, still ancient by human standards, but geologically younger than the rest of the Moon. Underneath the Moon's rocky shell lies a structure that resembles Earth's in some ways, but with key differences. The Moon has a crust, a mantle, and a small core, but the core is much less pronounced than Earth's. Its iron core is tiny and partly molten, accounting for only a small fraction of the Moon's volume. There's also no strong magnetic field. While the Earth has a powerful magnetosphere generated by the movement of molten iron in its core, the Moon's magnetic field is weak and patchy. But ancient rocks brought back from the Moon show that it once had a much stronger magnetic field, billions of years ago. What caused this magnetic activity and why it disappeared remains one of the Moon's lingering mysteries. Let's focus now on the Moon's impact history. Unlike Earth, where weather and geological activity erase the marks of time, the Moon's surface keeps its scars. Every crater, every ridge, every boulder tells a story. Some craters are small, shallow pits. Others are vast and complex, with central peaks and terraced walls. The largest impact basins span hundreds of miles. One of the most famous is the South Pole Aitken Basin, one of the largest and oldest known impact craters in the solar system. It stretches over 1,500 miles across and is nearly 8 miles deep. Scientists believe it may have exposed materials from deep inside the Moon, offering clues about its internal structure. Craters form when asteroids or comets strike the surface at incredibly high speeds, vaporizing on impact and blasting material outward. These explosions create shock waves that compress and heat the surface, forming the bowl-shaped depressions we call craters. Larger impacts can melt rock, fracture the crust, and even trigger volcanic activity. Over time, newer impacts overlap older ones, building a stratified history of collisions. Some craters are relatively fresh, with sharp rims and visible rays of ejecta, streaks of bright material thrown out by the force of the impact. Others are ancient and worn, softened by micrometeorite erosion and thermal cycling. The regolith, the Moon's powdery surface layer, plays an important role here. It's created over billions of years by constant micrometeorite impacts and the harsh effects of solar radiation. The result is a fine, gritty layer that blankets the moon like ash. It's made up of tiny fragments of rock, glass, and minerals, all broken down by time, and it's surprisingly deep. In some regions, the regolith can be over 30 feet thick. Beneath that lies a zone of fragmented rock known as the megaregolith, a deeper layer created by massive impacts that fractured the crust itself. But the moon is not just a passive recipient of impacts. It once had its own geological life. Evidence of ancient tectonic activity has been found in the form of lunar rills and faults, features that hint at internal stresses and crustal movements. These structures suggest that the moon once expanded and contracted, perhaps due to cooling of its interior or gravitational interactions with Earth. Today, the moon is geologically quiet, mostly. However, seismometers placed on the surface by Apollo astronauts detected small moonquakes. Some of these are caused by tidal forces from Earth, others by temperature fluctuations, and a few by meteorite impacts. The most intriguing moonquakes, called shallow quakes, can be strong, up to magnitude 5, and last for several minutes. Their exact cause is still uncertain. As we continue to explore, we're discovering more about the moon's complex past. Recent lunar missions have provided high-resolution images of the surface, revealing landslides, boulder trails, and possible lava tubes. Hollow tunnels formed by ancient volcanic flows. These tubes could be potential shelters for future astronauts, offering protection from radiation and temperature extremes. Another exciting development is the discovery of water molecules. For a long time, scientists believed the moon was completely dry. But in recent years, instruments on orbiters like India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter have detected signs of water in the form of hydroxyl and ice, especially in tumbled, hobbled, permanently shadowed craters near the lunar poles. This water is not liquid, but it's still a game changer. Water can be used for drinking, oxygen production, and even fuel if split into hydrogen and oxygen. If we can harvest it efficiently, lunar water could support long-term missions and make the moon a refueling station for deeper space exploration. It's clear that the moon is far more than just a dusty satellite. It's a geological archive, a cosmic witness, and perhaps even a stepping stone to other worlds. Its craters and rocks hold secrets not just about the moon itself, but about Earth, the solar system, and the formation of planets. And there's more to explore. In the next part of our journey, we'll explore the moon's gravitational connection to Earth, its mysterious far side, and how its motion affects our planet in ways we see, and some we don't. The moon and Earth are locked in a subtle but powerful gravitational dance, a relationship that has shaped both bodies for billions of years. To understand the moon is also to understand its deep influence on our planet, not just through tides, but through the very rhythm of life on Earth. Let's start with tidal forces. The moon's gravity pulls on Earth's oceans, creating two bulges, one on the side facing the moon and one on the opposite side. As Earth rotates, these bulges move around the planet, creating the rising and falling tides we experience daily. The sun also affects tides, but the moon's impact is stronger because it's so much closer. When the sun, moon, and Earth align, during new and full moons, we experience higher than normal tides, known as spring tides. When the moon is at a right angle to the Earth-Sun line, during the first and last quarter phases, we get neap tides, which are lower than usual. This gravitational relationship doesn't just affect water, it also subtly stretches the Earth itself, slightly deforming the crust. Over time, The moon's pull has even influenced Earth's rotation. In the early days of the solar system, Earth spun much faster. A full day may have lasted only 5 or 6 hours. But the moon's gravity created friction in the oceans, gradually slowing Earth's spin. As a result, the moon has been slowly drifting away from Earth, about 1.5 inches or 3.8 centimeters every year. That may not sound like much, but over billions of years, it adds up. When the moon first formed, it was much closer to Earth and appeared much larger in the sky. This also means that in the distant past, solar eclipses would have looked different, more dramatic, with the moon covering the sun more completely. Eventually, in the far future, the moon will be too far away to fully block the sun, and total solar eclipses will become a thing of the past. Now let's turn to the moon's orbit. The moon orbits Earth in an elliptical path, not a perfect circle, but slightly stretched out. This means the distance between Earth and the moon changes as it moves. When it's closest, we call it perigee. When it's farthest, it's called apogee. This is why the moon sometimes appears larger in the sky, especially during what's known as a supermoon, when a full moon coincides with perigee. It takes the moon about 27.3 days to complete one orbit around Earth. That's called a sidereal month. But the cycle of lunar phases, from new moon to new moon, is slightly longer, about 29.5 days. This is called a synodic month, and the difference is due to Earth's own movement around the Sun. The moon's orbital plane is tilted about 5 degrees relative to Earth's orbital plane around the Sun. This small tilt is why we don't have eclipses every month. Eclipses only occur when the Sun, Earth, and Moon line up closely enough, usually a couple of times a year. The Moon's orbit is also responsible for a fascinating phenomenon: tidal locking. This means the Moon rotates on its axis at the same rate that it orbits Earth, about once every 27 days. As a result, the same side of the Moon always faces Earth. This wasn't always the case. In its early history, the Moon likely rotated more quickly, but Earth's gravitational influence gradually slowed its spin until it became locked in this synchronized dance. Because of this, we can only ever see about 59% of the Moon's surface from Earth. Not just 50% because of a subtle wobble called libration. Libration allows us to peek a bit around the edges over time, revealing a little more of the Moon's hidden face. But what about the side we can't see? The so-called far side of the Moon has long captured imaginations. For centuries, no one knew what it looked like. Some thought it might be a lush, Earth-like paradise. Others imagined it to be a mirror image of the familiar face. In 1959, the Soviet Lunar 3 spacecraft sent back the first images of the far side. The reality was strikingly different. The far side is heavily cratered, rugged, and mostly lacks the large dark maria that dominate the near side. Scientists believe this difference is due to variations in crust thickness. The far side's crust is thicker, which may have prevented lava from breaking through and forming maria. The most prominent feature on the far side is the South Pole Aitken Basin, which we mentioned earlier. It's one of the largest impact craters in the solar system and is thought to have exposed material from deep beneath the surface. Studying this region could provide important clues about the Moon's interior and its early history. Another important region is the Moon's South Pole. Unlike the North Pole, which is relatively bland, the South Pole contains craters that never receive sunlight. These permanently shadowed regions are among the coldest places in the solar system, with temperatures dropping below -400 degrees Fahrenheit. In these deep shadows, scientists have detected deposits of water ice, a critical resource for future missions. Recent missions have focused on exploring these polar regions. India's Chandrayaan-2 and Chandrayaan-3, China's Chang'e missions, and NASA's Lunar Reconnaissance Orbiter have all contributed to mapping, measuring, and identifying potential landing sites near the Moon's poles. Beyond its orbit and geology, the Moon has helped shape Earth's very stability. One of its key roles is stabilizing Earth's axial tilt. Our planet tilts at an angle of about 23.5 degrees, which is responsible for the seasons. Without the Moon's gravitational influence, Earth's tilt could vary wildly over time, leading to dramatic shifts in climate and possibly making life as we know it much harder to sustain. The Moon acts like a stabilizing weight, a counterbalance that keeps Earth's rotation from wobbling too much. This stability may have been crucial in allowing complex life to evolve and thrive on our planet. Even in deep time, the Moon's presence has helped shape the biosphere in subtle ways. Some scientists believe that tidal pools, created by the Moon's pull, may have been important in the origin of life, allowing organic molecules to concentrate, interact, and eventually form the first self-replicating systems. In a way, the Moon has always been part of Earth's story. It formed from the same ancient collision, it orbits in resonance with our planet, and it affects our oceans, our calendars, and even our consciousness. Its slow orbit through the sky was one of the earliest clocks, long before humans had machines to measure time. We measure months by the Moon. In fact, the word month comes from moonth, and even today, many cultural and religious festivals are based on the lunar calendar, from Ramadan to Chinese New Year. As we gaze up at the Moon, we're not just looking at a lifeless rock, we're looking at a partner in Earth's evolution, a silent companion that has guided life in ways we're still beginning to understand. Humanity has gazed at the Moon for countless generations, not just with curiosity, but with longing. It became a symbol of dreams, of stories, and eventually of the impossible made real. For most of our history, the Moon was unreachable, a distant light in the night sky. But all of that changed in the 20th century. The story of humans reaching the Moon is one of ambition, risk, technology, and the will to explore. It begins not in space, but here on Earth during the Cold War, a time of fierce rivalry between the United States and the Soviet Union. That competition extended into space, in what became known as the space race. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. It was a beeping metal sphere about the size of a beach ball, but it marked the beginning of a new era. Just 4 years later, in 1961, Soviet cosmonaut Yuri Gagarin became the first human to orbit the Earth. The United States responded with bold determination. That same year, President John F. Kennedy delivered a now famous speech to Congress, declaring that America would send a man to the Moon and return him safely to Earth before the decade was out. At the time, it was an audacious goal. No human had even spent more than a few hours in space. To make this vision a reality, NASA developed the Apollo program, a monumental effort involving hundreds of thousands of people: engineers, scientists, technicians, pilots, and support staff across the country. It required designing entirely new kinds of rockets, spacecraft, computers, and life support systems. Before Apollo, NASA launched a series of test programs. Mercury proved humans could survive in space. Gemini developed critical skills like spacewalking and docking, necessary for more complex missions. By the late 1960s, the foundation was in place. Then came Apollo 11. On July 16, 1969, a massive Saturn V rocket launched from Kennedy Space Center in Florida, carrying astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins. 4 days later, on July 20th, Armstrong and Aldrin descended to the Moon's surface in the Lunar Module Eagle, while Collins remained in orbit aboard the Command Module Columbia. At 10:56 p.m. Eastern Time, Armstrong stepped off the ladder and spoke the words that would echo around the world. That's one small step for a man, one giant leap for mankind. For the first time in human history, a person stood on another world. Buzz Aldrin soon followed, describing the scene as magnificent desolation. The two astronauts spent just over 2 hours walking on the moon, collecting rocks, taking photographs, and deploying scientific equipment. They planted the American flag, though it wasn't meant to claim territory, but to symbolize achievement. They left behind a plaque that read, "Here men from the planet Earth first set foot upon the moon. July 1969 AD. We came in peace for all mankind." After 21 hours on the surface, they returned to Columbia and made the journey back to Earth, splashing down safely in the Pacific Ocean on July 24th. Apollo 11 was just the beginning. Over the next 3 years, 5 more Apollo missions, 12, 14, 15, 16, and 17, successfully landed astronauts on the moon. Each mission improved in duration, complexity, and scientific value. Apollo 12 landed near the Surveyor 3 probe, demonstrating pinpoint accuracy. Apollo 14 brought back nearly 100 pounds of rocks. Apollo 15 introduced the Lunar roving vehicle, a battery-powered moon buggy that allowed astronauts to travel miles across the surface. Apollo 16 explored the lunar highlands, and Apollo 17 in 1972 was the last mission, and included geologist Harrison Schmitt, the only professional scientist to walk on the moon. Altogether, the Apollo program brought back 842 pounds of lunar rocks, soil, and core samples. These samples revealed the moon's age, composition, and history. They helped confirm the giant impact theory of lunar formation and showed that the moon's volcanic activity ended long ago. The astronauts also left behind scientific instruments. Some measured moonquakes, others tracked solar wind or reflected lasers for precise measurements of the moon's distance. A few of these instruments continue to transmit data for years, but perhaps the most important legacy of Apollo was psychological and cultural. It showed what humanity could achieve when united by vision and purpose. Images of Earth from the moon, especially the famous Earthrise and blue marble photographs, reminded people of our shared home, small and fragile against the blackness of space. Despite Apollo's success, the program ended after Apollo 17. Political priorities shifted, budgets were reduced, and public interest waned. No humans have set foot on the moon since 1972. Still, the dream never died. Over the following decades, robotic missions kept the exploration alive. The Soviet Union continued to send unmanned landers and sample return missions. NASA sent orbiters like Clementine and Lunar Prospector, which mapped the moon's surface in detail. More recently, a new era of lunar exploration has emerged. Countries like China, India, and Japan have joined the effort, launching orbiters, landers, and even rovers. China's Chang'e program has been especially ambitious, landing on both the near side and the far side of the moon, the first in history to do so. NASA, too, has returned its focus to the moon. The Artemis program aims to land the next humans, including the first woman and the first person of color, on the lunar surface by the late 2020s. Artemis will also establish a sustainable presence on and around the moon, including a space station in lunar orbit called the Gateway. These missions will be different from Apollo in key ways. They will last longer, explore more diverse terrain, and make use of modern technologies like 3D printing, AI-assisted navigation, and reusable spacecraft. There's also an emphasis on international cooperation, with partners from Europe, Canada, and beyond. The goal isn't just to revisit the moon, It's to use the moon as a base for deeper space missions, a proving ground for life beyond Earth, a stepping stone to Mars, and eventually even farther. Private companies are also playing a role. Firms like SpaceX, Blue Origin, and others are developing vehicles and systems for cargo delivery, crew transport, and lunar infrastructure. The commercial space sector is helping to lower costs and increase innovation, opening the door to a new kind of lunar economy. Why go back to the moon? There are many answers. To learn more about the solar system's history, to test the limits of human endurance in extreme environments, to inspire the next generation of scientists, engineers, and dreamers, to search for resources that might support life on the moon and on worlds beyond. The moon is also a natural platform for science. Telescopes placed on its far side would be shielded from Earth's radio noise, offering an ideal location for deep space observations. The low gravity and vacuum environment make it a perfect laboratory for studying physics and materials. And then there's the emotional side. To stand on the moon is to feel the full scale of human achievement. To look back at Earth hanging in the void is to realize how connected we all are. The moon reminds us that we are part of something larger, a species capable of leaving its cradle, crossing vast distances, and setting foot on other worlds. We've only just begun to explore the moon. For all that we've learned, there are still countless questions. What lies beneath the surface? How can we live and work there sustainably? What stories are hidden in the layers of rock and ice? As our journey continues, we'll explore the scientific frontiers of the moon, its potential for research, for settlement, and for shaping the future of space exploration. The moon may seem quiet and unchanging, but scientifically, it's one of the most valuable objects in the solar system. Studying the moon offers a window into planetary formation, geological evolution, and even the origins of life. In this part, we'll explore the science we've gained from the moon and the deeper questions that continue to emerge with every mission. Let's begin with lunar geology, the study of the moon's structure, composition, and history. Much of what we know today comes from the Apollo missions. The rock samples brought back to Earth have been studied for over 50 years, and they continue to yield new insights. One of the most important discoveries was the confirmation that the moon is incredibly ancient, older than most Earth rocks. The oldest samples date back over 4.4 billion years, offering a record of the early solar system that's been erased on Earth by erosion, tectonics, and weather. These rocks showed clear evidence of two major processes: widespread volcanic activity and an intense period of impacts, known as the Late Heavy Bombardment. This violent chapter in the solar system's history occurred around 3.8 to 4.1 billion years ago, when countless asteroids and comets slammed into the inner planets. The moon preserves a record of this bombardment. Its surface is scarred with craters and basins from this period, many of which were later flooded with lava to form the smooth Maria. Earth was hit just as hard, maybe even harder, but our dynamic surface erased most of the evidence. The moon, in contrast, holds the memory of these ancient collisions. Lunar scientists also learned about the moon's internal structure. Seismic instruments left by Apollo astronauts detected vibrations known as moonquakes. These helped map the interior, revealing a thin crust, a thick mantle, and a small core, a structure broadly similar to Earth's, but with key differences. For example, the moon's core is proportionally much smaller and less active. This explains its lack of a global magnetic field today. However, some ancient lunar rocks show evidence of magnetism, suggesting that the moon once had a molten, convecting core capable of generating a magnetic field, possibly billions of years ago. Lunar dust has also revealed clues. The fine powder covering the surface, the regolith, is made up of crushed rock, volcanic glass, and tiny bits of metal formed in the intense heat of impacts. It tells us not only about the moon's geology, but also about the space environment itself, how solar radiation and micrometeorites affect airless worlds over time. Another major discovery in recent years is the presence of water. For decades, scientists believed the moon was bone dry. But in 2009, instruments on board NASA's L-Cross mission confirmed the existence of water ice in permanently shadowed craters at the lunar South Pole. These regions, hidden from the sun's rays for billions of years, act as cold traps, preserving ice that may have come from comets or from volcanic outgassing. Even more exciting, tiny amounts of water molecules have been found spread across the lunar surface, especially in cooler regions. While it's not liquid water, more like chemically bound hydroxyl, OH molecules, its presence suggests that the moon is not as dry as once thought. This discovery has huge implications. Water is essential for sustaining human life, but it's also a potential source of fuel. Through a process called electrolysis, water can be split into hydrogen and oxygen, the same elements used in rocket propulsion. If we can learn to extract and process lunar water, it could reduce our need to launch supplies from Earth, making deep space missions more sustainable. Another area of interest is the moon's potential to reveal the solar system's deeper history. Because the moon lacks weather, erosion, and active plate tectonics, it preserves ancient materials on or near the surface. Some regions may contain clues about the earliest building blocks of planets, the chemistry of the early solar system, and even the origin of Earth's atmosphere. The moon may also help answer questions about the origins of life. Some scientists believe that organic molecules, the basic ingredients of life, could be preserved in shadowed regions or within buried layers of ancient regolith. If so, these could tell us whether the chemistry of life is common in the solar system or unique to Earth. There are also important medical and biological questions tied to lunar science. The moon's gravity is only 1/6 that of Earth's. Long-term exposure to low gravity could have unknown effects on the human body, including bone loss, muscle atrophy, and changes in fluid distribution. Understanding these effects is crucial before we attempt longer missions to Mars or beyond. Experiments on the moon could also help us understand radiation exposure in deep space. Unlike Earth, the moon has no atmosphere or magnetic shield to block harmful cosmic rays and solar particles. Future lunar habitats will need protection, and studying the environment firsthand will help design better shielding for astronauts. Beyond geology and biology, the moon is a perfect place for physics experiments. The lack of atmosphere and seismic noise makes it an ideal environment for sensitive instruments. For instance, telescopes on the far side could observe the universe in radio frequencies that are blocked on Earth. Astronomers have proposed placing observatories there to study the early universe, dark matter, and distant galaxies with unprecedented clarity. Even simple tools have taught us a lot. Reflectors placed on the moon during Apollo missions are still used today. By bouncing lasers off these mirrors, scientists can measure the exact distance between Earth and the moon with millimeter precision. These experiments help refine our understanding of gravity, Earth's rotation, and even the theory of general relativity. More advanced tools are on the way. Robotic landers and rovers will carry ground-penetrating radar, spectrometers, and drills to analyze the moon's surface and subsurface. Orbiters are mapping the terrain in high detail, identifying mineral deposits and possible landing sites for future missions. Private companies are beginning to contribute as well, launching small science payloads in coordination with space agencies. These efforts aim to make lunar science more accessible and more continuous, reducing costs and increasing the pace of discovery. There's also a philosophical side to lunar science. The moon is a place of paradoxes, ancient and untouched, yet central to human history. It's a world without air or water, yet it shapes our tides and calendars. It's barren, but filled with potential. The more we study it, the more we realize how much it has to teach us, not just about itself, but about Earth, the solar system, and life itself. And there's still so much we don't know. What's hidden beneath the crust? Are there large lava tubes that could one day shelter humans? How pure and abundant is the polar ice? Could the moon's surface materials be used for construction or manufacturing? As we prepare to return to the moon with new tools, new goals, and new dreams, lunar science will be at the heart of everything. Every footprint, every sample, every measurement brings us closer to understanding not just the moon, but the universe itself. After more than 5 decades since humans last set foot on the moon, we are now entering a bold new chapter. Governments, private companies, and international partnerships are all planning to return, not just to visit, but to stay. The vision for this new era is not just about planting flags or collecting rocks, but building a lasting presence on the lunar surface. The cornerstone of this effort is NASA's Artemis program. Named after the twin sister of Apollo in Greek mythology, Artemis aims to return humans to the moon and establish a sustainable base of operations. The goals are clear: land the first woman and the first person of color on the moon, build infrastructure for long-term exploration, and prepare for future missions to Mars. Artemis begins with a powerful rocket system called the Space Launch System, or SLS, the most powerful rocket NASA has ever built. It will carry the Orion spacecraft, designed to transport astronauts to lunar orbit and beyond. Artemis Wevbot, the first uncrewed test flight, successfully orbited the moon and returned to Earth, paving the way for future missions. Artemis II will carry astronauts around the moon, testing life support and navigation systems. Then, Artemis III will attempt a crewed lunar landing near the South Pole, a region never visited by humans. This area is of great interest because of the presence of water ice and long periods of sunlight, which are ideal for establishing a base. Unlike the Apollo missions, which lasted only a few days, Artemis aims for long-duration stays. Astronauts will live and work on the surface for weeks at a time. They'll build habitats, test new technologies, and learn how to survive in the harsh lunar environment. One of the most exciting parts of the Artemis plan is the Gateway, a small crewed space station that will orbit the moon. The Gateway will serve as a staging point for landings and a hub for science and communications. It will also support international cooperation with modules and contributions from the European Space Agency, the Canadian Space Agency, and others. Lunar landers will carry astronauts from the Gateway down to the surface and back. NASA has selected commercial partners, like SpaceX, to develop reusable landers. SpaceX's Starship is one of the contenders, designed to carry large payloads and crews to the moon and potentially to Mars. But Artemis isn't the only effort underway. China has its own ambitious lunar program. After successful Chang'e missions, including landing on the far side of the moon, China plans to send taikonauts, Chinese astronauts, to the lunar surface in the 2030s. China and Russia have also proposed building a joint International Lunar Research Station, a long-term base at the moon's south pole. India, Japan, South Korea, and the United Arab Emirates are investing in their own lunar missions, from orbiters and landers to robotic rovers. This international momentum is transforming lunar exploration into a global effort, with shared science and diverse ambitions. At the same time, private companies are reshaping how we reach the moon. NASA's Commercial Lunar Payload Services (CLPS) program hires private companies to deliver scientific instruments, tech demos, and tools to the lunar surface. These robotic missions will scout terrain, test hardware, and deliver essential supplies before astronauts arrive. Astrobotic, Intuitive Machines, Firefly Aerospace, and others are building lunar landers capable of carrying small payloads. These missions will help develop the logistical and commercial infrastructure needed for long-term exploration. One of the most critical challenges for returning to the moon is survival. Unlike Earth, the moon has no atmosphere to regulate temperature. It gets scorching hot in sunlight, over 250 degrees Fahrenheit, and freezing cold in darkness, dropping below -200 degrees. These temperature swings occur over a lunar day, which lasts about 29 Earth days. This means future lunar bases must endure long, harsh nights and protect astronauts from extremes. Radiation is another major concern. Without a magnetic field, the moon is exposed to solar flares and cosmic rays. Future habitats will need shielding, potentially by burying structures under regolith or building them into lava tubes. Water, polyethylene, and other hydrogen-rich materials may also help absorb radiation. The moon's gravity, about 1/6 that of Earth's, is another unknown. We don't yet fully understand how low gravity affects the human body over months or years. Long-term lunar missions will provide valuable data on muscle loss, bone density, and how to adapt human health systems to different environments. Then there's the issue of dust. Lunar regolith is extremely abrasive and sticky. It clings to suits and equipment, causing wear and contamination. Future missions will need better suit designs, dust-proof mechanisms, and advanced cleaning systems to mitigate the impact of this fine powder. To support extended stays, we'll also need resources, especially water, oxygen, and energy. Water ice at the poles may be harvested and purified. Oxygen can be extracted from lunar soil, which contains oxides in minerals like ilmenite. Solar energy will likely be the main power source, especially in areas of near-continuous sunlight. Another key development is in situ resource utilization, or ISRU, using local materials to build infrastructure. Lunar soil could be turned into bricks, concrete, or even 3D printed structures. This reduces the need to launch heavy materials from Earth, cutting costs and increasing independence. Food production is another frontier. Future lunar habitats may include hydroponic or aeroponic systems, growing plants without soil. These systems recycle water and air, provide fresh food, and support the psychological well-being of astronauts. All of these technologies, energy, water, construction, food, waste recycling, are being developed right now. They'll be tested not just for lunar missions, but for future journeys to Mars, where self-sufficiency will be even more critical. In time, we may see the first permanent human presence on the moon. Small bases could grow into research stations, science labs, and even commercial outposts. Lunar tourism, mining, and manufacturing may one day become part of a lunar economy. And if we succeed in living on the moon, we'll take with us not just tools and supplies, but ideas about cooperation, sustainability, and what it means to be human in space. The moon could also become a hub for deep space travel. Launching from the moon requires far less energy than from Earth thanks to its low gravity. It could serve as a fuel depot, a construction yard, or even a gateway to Mars and the outer planets. But perhaps the greatest benefit of returning to the moon is perspective. Standing on the moon, looking back at Earth, astronauts speak of something called the overview effect, a sudden realization of the fragility of our planet and the unity of all people. It's a powerful reminder that we are part of one world and one story. The moon calls us forward, not just to explore, but to learn, to grow, and to reach for something greater than ourselves. In the next part of our journey, we'll explore the moon's cultural impact, how it's shaped mythology, art, calendars, and the way we understand time and meaning. Long before telescopes, rockets, or astronauts, the moon held a special place in the hearts and minds of people across the world. It was more than a light in the night sky. It was a guide, a calendar, a deity, a storyteller. In every culture, on every continent, the moon has inspired myths, rituals, poetry, and wonder. The earliest human societies didn't just observe the moon, they built their lives around it. Its phases provided a reliable pattern that guided agriculture, hunting, and social events. The lunar cycle, roughly 29.5 days, became the basis for some of the world's first calendars. The word month comes from munth, a direct reflection of how ancient people tracked time. Even today, many of our major cultural and religious observances are based on lunar calendars. Islamic months begin with the sighting of the new crescent moon. Jewish holidays like Passover and Hanukkah follow a lunisolar calendar. Chinese New Year, the Mid-Autumn Festival, and other East Asian celebrations also follow the rhythm of the moon. But the moon has always meant more than just timekeeping. To many, it was alive, a divine or spiritual presence in the sky. In ancient Egypt, the god Khonsu was associated with the moon, healing, and time. In Mesopotamia, the Sumerian moon god Nana, later known as Sin, was worshipped as a powerful celestial ruler. These early lunar deities were often seen as guides through the night, protectors, or symbols of renewal. In Greek mythology, the moon was personified as Selene, a radiant goddess who rode a silver chariot across the sky. Her Roman counterpart was Lunar, from which we get words like lunar and lunatic. Artemis, the goddess of the hunt, was also associated with the moon, especially in her connection to wild nature and independence. In Hindu tradition, Chandra is the moon god, cool, reflective, and gentle. He rides a chariot pulled by antelopes and is connected to fertility and the mind. In Chinese law, the moon is home to the jade rabbit and the moon goddess Chang'e, who is said to live there in solitude after drinking an elixir of immortality. Across the Pacific, in Polynesian stories, the moon is a place of transformation and dreams. The Maori of New Zealand tell of Rona, who was taken to the moon and became part of its face. In many Native American cultures, the moon was seen as a counterbalance to the sun, mysterious, feminine, and powerful. The moon's face, with its craters and Maria, gave rise to countless interpretations. Some saw a man carrying a bundle of sticks, others saw animals, faces, or even landscapes. These stories gave meaning to the moon's appearance and helped encode traditions through generations. In literature and art, the moon has always been a symbol of emotion, mystery, and the unconscious mind. It's associated with love and longing, madness and magic. Poets have written to the moon as a distant friend, a witness to sorrow, or a keeper of secrets. In William Shakespeare's plays, the moon is a symbol of transformation and fate. In Persian poetry, it's a metaphor for beauty and the beloved. Romantic artists painted moonlit landscapes to evoke a sense of awe and melancholy. In music, the moon has inspired everything from Beethoven's Moonlight Sonata to jazz standards like Blue Moon. The moon is also central to folklore and superstition. Many cultures believe the full moon affected human behavior, causing restlessness or madness, hence the term lunatic. Others believed it was a time when magic was strongest, when dreams were more vivid, or when the boundary between worlds became thin. Farmers planted crops by the phases of the moon. Sailors watched its rise and fall to guide them at sea. And lovers have long walked by moonlight, drawn to its soft glow and romantic pull. Even in modern times, the moon's cultural power hasn't faded. In film and literature, it's often portrayed as a place of mystery or revelation. In fantasy, it's a portal or a prison. In science fiction, it's a colony, a battleground, or a stepping stone to the stars. Consider how often the moon appears in children's books. A destination for curious minds. A quiet companion in the night sky. It's featured in lullabies, bedtime stories, and nursery rhymes. The cow jumped over the moon. I see the moon and the moon sees me. These phrases echo across generations. And then there's the moon's role in science communication and inspiration. For many people, watching the moon through a telescope is their first real encounter with the universe. Its craters, shadows, and changing phases reveal that space isn't just an abstract idea. It's real, and it's close. That proximity matters. The moon is the only celestial body where we can see surface features with the naked eye. It's a visible world, not just a point of light. Its slow movement across the sky is calming, predictable, and timeless. In this way, the moon has always served as a bridge between the known and the unknown, between Earth and the cosmos, between the human and the divine. In times of uncertainty or change, people often look to the moon for a sense of grounding. It has witnessed every chapter of human history. It was there when the first humans walked upright. It was there during every war and every peace. It was there before the first written word, and it will be there long after the last one is spoken. And yet, despite its familiarity, the moon never becomes mundane. It reflects sunlight, but somehow glows with its own kind of magic. It reminds us that beauty can exist in silence. That mystery doesn't need to be solved to be felt. In many ways, our relationship with the moon is as emotional as it is scientific. It connects generations, cultures, and disciplines. It's both an object of study and a mirror of ourselves. As we prepare to return to the moon with rockets and robots, we also return with stories, dreams, and myths, the soft payloads of the human spirit, and those will be just as important to carry forward. The moon is not just a companion in the sky, it is a deeply influential force that has shaped the Earth's environment, climate, and even the development of life itself. Though often overlooked, its effects are profound, subtle, and in many ways essential to the stability of our planet. Let's begin with tides, the most visible way the moon affects Earth. Tides occur because of the gravitational pull the moon exerts on Earth's oceans. On the side of Earth facing the moon, the water is pulled slightly toward it, creating a bulge, a high tide. On the opposite side, inertia causes another bulge. As Earth rotates, these bulges move around the globe, leading to regular rises and falls in sea level. Most coastal areas experience 2 high tides and 2 low tides every day. This movement of water has immense implications. Tides stir the oceans, mixing nutrients and oxygen, which helps support marine ecosystems. In intertidal zones, where the land meets the sea, the regular exposure and submersion of shoreline creates dynamic environments filled with life that has adapted to the rhythm of the moon. Tidal patterns also influenced early navigation and fishing, guiding human activity long before modern science explained how it all worked. Ancient cultures used the moon to understand when to plant crops, go fishing, or predict floods. Even today, farmers, sailors, and coastal engineers rely on tidal charts based on the moon's motion. But the moon's influence doesn't end with the tides. It also plays a crucial role in stabilizing Earth's rotation. Our planet spins on a tilted axis, about 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us seasons. However, without the Moon, that tilt would be far less stable. Over long timescales, gravitational interactions with the Sun and other planets can cause a planet's axis to wobble or shift, a phenomenon called axial precession. For Earth, the Moon acts like a stabilizer, holding our axial tilt within a narrow range. This keeps our climate relatively stable over tens of thousands of years. Without the Moon, Earth's tilt might swing wildly, perhaps even tipping over entirely. Such changes would bring dramatic shifts in climate, turning poles into tropics and deserts into ice fields. This kind of instability could make life much harder to adapt and survive. In this way, the Moon may have created the conditions for complex life to evolve and thrive. Its presence kept Earth's seasons regular and predictable, allowed ecosystems to develop consistent patterns, and reduced the environmental chaos that might otherwise have disrupted evolution. But there's more. The early Moon, newly formed from a colossal impact, would have loomed large in Earth's sky, several times wider than it appears now. Its gravitational pull was stronger, and the tides were more extreme. Some scientists believe these early, massive tides played a critical role in the origin of life. In shallow tidal pools, water would evaporate under the Sun, concentrating organic molecules. Then, as the tide returned, it would mix and reactivate those molecules. This wet-dry cycle may have been ideal for kick-starting complex chemistry, a possible step toward the formation of life. Over time, as the Moon receded and Earth's spin slowed, the tides became less dramatic, but the early Moon's influence may have already done its part. It may have helped concentrate the ingredients of life, provided energy through movement, and shaped the first habitats on Earth. The Moon also affects Earth's rotation in other subtle ways. Today, a full Earth rotation, one day, lasts 24 hours. But when the Moon first formed, Earth was spinning much faster. A day may have lasted only 5 or 6 hours. The Moon's gravity pulled on Earth's oceans, creating friction that slowly transferred energy from Earth's spin to the Moon's orbit. This caused Earth to slow down, and the Moon to move farther away. This process continues today. The Moon is drifting away from Earth at a rate of about 1.5 inches, or 3.8 centimeters per year. Over millions of years, this adds up, and as the Moon recedes, Earth's rotation will continue to slow, making days gradually longer over geologic time. This means that billions of years from now, a day on Earth could last more than 30 hours. The Moon will appear smaller in the sky, and total solar eclipses, which depend on the Moon being the same apparent size as the Sun, will no longer be possible. In that way, the Moon is not only a part of our past, but a marker of time itself. Its retreat is slow and steady, like the ticking of a cosmic clock. The Moon also influences Earth's biosphere in less obvious ways. Some animals use the Moon to navigate or time their behavior. Sea turtles, for instance, hatch under moonlight and use its glow to find the ocean. Coral reefs often synchronize their spawning with the full moon. Certain species of birds, fish, and insects follow lunar cycles, suggesting that the Moon's light and rhythm are deeply embedded in biological systems. Even human biology shows hints of lunar influence. The average menstrual cycle is about 29.5 days, the same as the lunar cycle. While the connection is debated, it's a reminder of how the Moon's rhythm may echo in our own biology. Psychologically, the Moon has long been linked to emotion and mood. The word lunacy comes from luna, the Latin word for moon, reflecting the ancient belief that the full moon could affect human behavior. While modern science doesn't support strong links between the moon and mental health, the symbolism remains powerful. Astronomically, the moon also helps shield Earth from space debris. Its gravity slightly affects the trajectories of asteroids and comets that pass nearby. While it's not a perfect shield, the moon has taken many hits, as its cratered surface shows, that might otherwise have struck Earth. In the far future, the moon's role in Earth's system will continue to evolve. Its slow retreat will change the dynamics of tides, length of days, and potentially even Earth's wobble. These changes are slow, taking millions of years, but they are reminders that our planet is not isolated, but part of a larger system in constant motion. The moon is often called a satellite of Earth, but it is more than that. It is a stabilizer, a timekeeper, and perhaps even a midwife to life. It has shaped the tides, the climate, and the spin of our world. And in doing so, it has helped create the conditions for everything we know, including ourselves. The moon is not just a destination, it's a scientific platform, a natural laboratory, and a window into the deepest questions of the cosmos. Because of its unique environment and history, the moon offers opportunities to conduct research that are either impossible or extremely difficult to carry out on Earth. In this part, we'll explore how the moon could help us better understand physics, astronomy, and the origins of the solar system. Let's begin with the moon's most basic advantage, its silence. The moon has no atmosphere, no weather, and virtually no geological activity. It is quiet in a way Earth can never be. That quietness makes it ideal for certain types of sensitive experiments, especially in radio astronomy and particle physics. On the far side of the moon, the hemisphere that always faces away from Earth, the surface is shielded from the constant buzz of human-made radio waves. This makes it the quietest radio environment in the inner solar system. Scientists have long dreamed of building a radio observatory there, capable of detecting low-frequency signals from the early universe, signals that are completely drowned out on Earth. Such an observatory could peer back to a time just after the Big Bang, when the first stars were forming and the universe was still in its infancy. By detecting the faint radio glow of hydrogen gas from this era, scientists could test theories about cosmic inflation, dark matter, and the structure of the early cosmos. The moon is also a good place to test the limits of general relativity and gravitational theory. Because the moon has such a stable, predictable orbit and is relatively close to Earth, it's ideal for high-precision measurements of gravity. One experiment already in progress involves laser reflectors left on the lunar surface by Apollo missions. Scientists on Earth bounce laser beams off these reflectors to measure the exact distance between Earth and the moon, down to the millimeter. These measurements help confirm aspects of Einstein's theory of general relativity. They also allow us to track tiny changes in Earth's rotation, gravitational field, and the moon's orbit. Over time, these data can reveal whether the fundamental constants of physics are truly constant or slowly changing over cosmic timescales. The moon's surface is also a geological time capsule. Because it lacks erosion, tectonic plate movement, and a protective atmosphere, the moon preserves ancient materials on or near the surface. Some scientists believe that certain parts of the moon's crust may contain preserved remnants from the early Earth, or even from other planets. There's also the tantalizing possibility that the moon has recorded the history of the solar system in its regolith. Every micrometeorite, solar flare, or burst of cosmic radiation that struck the moon left a mark. Layer by layer, these impacts built up a stratified record of space weather stretching back billions of years. Studying these layers could help us understand how the sun has changed over time, how often nearby supernovae occurred, and how Earth's environment has been influenced by space conditions. In this way, the moon is not just a record of its own history, but of the broader solar system and the galactic neighborhood. And then there's the mystery of volatiles, substances that vaporize easily, like water, carbon dioxide, methane, and ammonia. These elements are critical for life and planetary development. Discovering their sources and distribution on the Moon could offer clues to how they arrived on Earth. Was water delivered by icy comets? Did it emerge from volcanic activity? Or was it present in the original material that formed Earth and the Moon? By analysing lunar ice and the isotopic ratios within it, scientists can trace the origin of these substances and build models of how Earth got its oceans, and possibly how other planets might do the same. There's also interest in using the Moon as a proving ground for future science missions, not just for telescopes, but for planetary science, biology, and even quantum experiments. For example, future lunar laboratories might study how DNA responds to long-term cosmic radiation, or how microbial life behaves in partial gravity, or how quantum entanglement functions in a low-noise environment. These are questions we can't fully answer on Earth, and the Moon may offer the perfect test bed. Another advantage of the Moon is its location, close enough to Earth for communication and resupply, but far enough to provide a truly space-based perspective. A Moon-based telescope, for instance, wouldn't be blocked by Earth's atmosphere, clouds, or light pollution. It could operate continuously, capturing sharp images across a wide range of wavelengths. Some scientists have proposed building a giant infrared telescope inside a permanently shadowed crater, where temperatures stay extremely low, ideal for detecting faint heat signatures from distant galaxies, planets, and cosmic dust. Others have suggested using the Moon's gravity to help construct and launch large space telescopes or deep space probes. The Moon could also play a role in understanding time itself. Atomic clocks, the most precise timekeeping devices ever created, could be tested on the Moon to measure time dilation under different gravitational conditions. This would offer a rare opportunity to refine our models of space-time and gravity, pushing the boundaries of what we know. And let's not forget the Moon as a base for exploration. By establishing a sustained human presence, we can study how technology, infrastructure, and biology function over long durations in a harsh environment. We can test habitats, power systems, communication protocols, and life support, all of which will be needed for missions to Mars or even the outer solar system. In this way, the Moon becomes not just a destination, but a launch pad for the future. A place where we take our first serious steps toward becoming a multi-planetary species. And while science often focuses on the material and the measurable, the Moon also invites philosophical questions. What does it mean to explore? What is humanity's role in the universe? Are we alone? These are questions the Moon cannot answer directly, but by encouraging us to ask them, it becomes a catalyst for curiosity, for reflection, and for dreaming. The Moon has always been with us, but we are only just beginning to understand its full potential. As a source of scientific discovery, it may be one of the most valuable bodies in the solar system. The Moon has been watching over Earth for more than 4 billion years. It has pulled at our tides, steadied our climate, and perhaps even helped life take its first steps. It's shaped the rhythms of the natural world and the flow of human history. Long before we knew what it was made of or how it formed, we looked up and felt something timeless. Now, in our age of rockets and science, we've touched the Moon with our machines and even with our own hands. But the mystery has not faded. In fact, it has deepened. Every discovery reveals 1,000 more questions. Every mission, a new challenge. Every glance through a telescope, a quiet reminder that something so familiar can still be so unknown. In our time, the Moon is becoming more than a destination. It is a proving ground, a place to test our technology, our courage, and our ability to work together. It is a classroom, teaching us about the history of the solar system. It is a mirror reflecting both the brilliance and fragility of human ambition. But perhaps most of all, it is a threshold. The moon is the first step in something much larger. If we learn to live there, sustainably, respectfully, and wisely, we will have passed one of the great tests of civilization. We will have proven that we can exist beyond Earth not as conquerors, but as caretakers. Not in opposition to nature, but in harmony with the cosmos. In the years ahead, we will return to the moon with astronauts and robots. We will build habitats, grow food, and search for water. We will look back at Earth and feel its preciousness in a new way. We will look up at the stars from the lunar surface and feel how vast the universe truly is. We will mine data, not just resources. We will share knowledge across borders. We will write new stories, not just of flags and footprints, but of science, cooperation, and imagination. Children will grow up seeing the moon not as a distant, unreachable world, but as a real place. A place people live, work, and dream. And maybe, just maybe, from that quiet surface, we'll look outward again, toward Mars, toward Europa, toward the distant exoplanets circling other suns. And we'll say, we started here, on this ancient, cratered rock. This was our training ground. This was our first outpost. This was where we learned to become something more. The moon doesn't shine on its own. It reflects the light of the sun, and perhaps also the light of us, our curiosity, our courage, our capacity to wonder. So the next time you see the moon rising in the night sky, take a moment to remember everything we've discovered. Beneath its stillness is a story billions of years in the making, a story written in dust, in silence, in motion, and now in our own voices and footprints. It is a place we've been, a place we are going, and a place we will always carry with us. Thank you for joining us tonight here on SleepSpace. We hope this journey through everything we know about the moon has been both informative and relaxing. As you drift into sleep, let your mind float gently as if orbiting, calm, weightless, and at peace. Good night, and keep dreaming.